several unpackers that are used by AV companies to analyze the malware. They all have their own little private unpacker, writing several to deal with the malware analysis. Which brings me to my next topic, how to go about implementing an automated unpacker. So I wanted to be as generic as possible. I chose a approach that uses full system emulation. I used a unpacker called Bochs. Sorry, not unpacker, an HPC emulator called Bochs, which is just a program written in C++ that emulates all kinds of hardware devices, and for every CPU instruction there is, it has its own little C++ method that emulates its behavior and reflects it onto the internal CPU state. On Bochs, I ran a fully unmodified Windows XP guest system because I wanted my unpacker to be as unobtrusive as possible. So I want to be there as little way as possible for the guest operating system or for the malware sample I want to execute there to detect that it's running in an analysis environment. I know it is possible to detect emulators or virtual machines, but when you deal with this kind of analysis, I don't think there's much you can do about that fact, except building better emulators. For my unpacker that's not running any code within the guest system to be actually able to have a look at processes, their features, and monitor their execution, the unpacker needs to be aware of guest operating system semantics. It needs to know which process is currently active, what libraries are there, what's it doing currently. In the end, I wanted to be able to generate valid PE files from the unpacker result. And valid can mean two things. First thing is that they are syntactically correct. That means they are legal according to the Microsoft PE specification. And this is important if you want to use the PE file or the reconstructed file within other analysis tools like either Pro or HT, stuff like that. And then I took some more steps to at least try and reconstruct executable PE files. So take the unpacking result and reconstruct the PE file that would actually go and execute if you just started on a Windows system. And for that important is OEP detection, which we get to that later, and one other challenge was termination, that is when to stop unpacking. When are we done? But back to Bochs. Bochs can instrument certain events out of the box, like modification of the CR3, which is the page directory base register. We briefly heard it earlier. Bochs can instrument memory accesses, for us of importance on memory writes, and it can monitor branch instructions. This is basically all we need for unpacking. And how does Bochs do that? This is a quote from the Bochs Developers Guide. A complaint about the many macros that mangle the Bochs source code. It's really quite horrible to read at times, but macros are also the core feature of Bochs' instrumentation features. You have just this set of macros. These are just placed within the source code whenever something instrumental happens. Like at the top we see this is for operations that affect the translation of the side buffers. This macro is called with the CPU ID, what the reason is of the TLB modification, and it's applicable in the CR3 register value. Then we have some functions that deal with branches. Again, CPU ID contains the new instruction pointer, and sometimes even the new instruction pointers. And last but not least, linear memory access. That means whenever a process or the guest system writes to memory or reads from memory, we get notified of which CPU it is The linear address, physical address, the length of the memory write for each dictator would be 1, 2, or 4 bytes, and what is the read or write of both. These are there are several more instrumentation events. You can get notified whenever the box is done decoding an instruction, or you can just monitor physical memory accesses alone and all kinds of stuff. During my implementation, after I had a first prototype, I noticed C++ is not my language. I ended up writing more code to maintain data structures than I was actually adding functionality. So I decided I would like to try and implement this all in Python. And this actually works fairly well. What I do is I just link Box against the Python interpreter library, and then Box has its own set of functions defined and made known to the Python interpreter that can access the internal state of the emulator, like can read memory, can access registers and stuff like that. And when the emulator starts up, it imports a certain module that is implemented in Python. So this is where all the actual functionality resides. So we have the counterparts to these macros are actually then called exported. The x58 memory management unit uses certain data structures called page directories and page tables, because you can't this is how it works. We'll get to that in a bit. And the page directory base register contains the physical address space of the active page directory. So every virtual address space layout there is